Okay, so bonjour, hello everyone. So it's our pleasure to have today Bowen for the GERAD seminar. So Bowen is a candidate to become a member, a regular member of GERAD. So a few words about Bowen before we start, maybe. So Bowen is recently joined Polytechnique as an assistant professor in automation. He works on nonlinear systems in general, estimation, system identification. That's going to be the topic of the talk today. He finished his PhD. He did his PhD at Shanghai Jiaotang.
Yeah.
And during his PhD, he spent a couple of years, or maybe a year and a half, at CNRS in Gilles-sur-Yvette in France, working with Romeo Ortega. And then after that, he spent a few years as a postdoc in Australia at Sydney University, right?
Yeah.
So with people that we know in robotics in particular, so his work has application to robotics and energy systems. And so I think there could be interesting collaborations that we can develop here at GERAD. So we're happy to have you today and to present it. Thank you.
Thank you, Jihong. Thank you for having me. Today, it's my great pleasure to being here. So actually, I know the name of GERAD many years ago. Before, during that period, I never visited Canada, but I know the name of GERAD from Jihong's paper. So what I'm going to talk about today is our recent results with my former postdoc supervisor in Manchester and the PhD student Fletcher Fan. So it's our quite recent result. Some work just accepted last month, and some work are still under review. I'm going to talk about the relationship between two methods. One is contraction analysis. The other one is Koopman operator. So they provide two methodologies to analyze nonlinear system by means of linear system theory. Okay, so let's get started from some facts in control engineering. So as you know, it's quite fair to say almost all systems in engineering are nonlinear. So it can be a static system or dynamical system. And we know analysis of linear system is much easier than the nonlinear part. So we can use the linear system to approximately get the behavior of the nonlinear one. For example, we can do the first order linearization by calculating the Jacobian matrices of the system. And this is widely exploited in control filtering and optimization. But it brings many drawbacks. For example, the linearization just provides a very local information. So it's very hard to get some global information, or in many cases, if we do not need the global one, we would like to know the behavior of the system in a very large domain. So this is not possible if we only do the first order linearization. On the other hand, contraction analysis and Koopman operator provide two methodologies that can be used to analyze nonlinear system by means of linear system theory exactly and globally. So what I refer to exact and global, it means we do not do any linearization. So it's the accurate description of the system. So previously I worked on very traditional nonlinear control stuff. And so this direction is very popular in France and Italy. There are some European schools. But just in the last few years, I realized these two methodologies are very useful for other community. So, I just talked to many people from other fields like robotics, aerospace, and power system. So they do have the need to employ the nonlinear control theory in their task like control and estimation. But it's very very time-consuming to learn nonlinear control theory because they need to do other tasks to do the mechanical design, and also they are also use some time on the material design. And it's very good way to do some collaboration. And one way is for some control people, we can provide the plug and play methodology for them, and they only try to use this kind of methodology in their analysis because linear system is very easy to understand for people from other community. Actually, contraction analysis and Koopman are both neither are particular in their basic idea. So for the Koopman operator, it may take back to about 1 century ago. And for the contraction analysis, it was first employed by Lewis' paper. It's also more than maybe 80 years ago. But at the moment, both of them are enjoying the resurgence, in particular in popularity in recent years. Okay, so in my talk, I'm going to start with some preliminary background of the Koopman operator and contraction analysis. Then I will show you our finding about the relationship between the two approaches. And then I will apply the methodology in two applications that we are trying to use the data to learn the contraction metric and also the stable Koopman embedding. So if I have time, I will show some extension of the theoretical finding. Okay, so let's get started from the preliminary background of the Koopman operator and contraction analysis. The Koopman operator is actually the eigendecomposition, is an extension of the eigendecomposition of a linear system. So in the linear system theory, we know for a linear time invariant system in the form like dot x equal to x, we can say the very simple case that matrix A is diagonalizable. For this case, we can decompose A with the eigen value from λ1 and lambda n. So the solution of this system is given by the model decomposition with the mode from λ1 to lambda n, and here Vk and Rk are the right and the left eigenvector of the original system. For the more general cases, we also learn with the conjugate eigenvalue is not so difficult to do extension. Okay. So the Koopman operator is the extension to nonlinear system. We consider the nonlinear autonomous system in the form x dot equal to fx, and we denote a solution at time t if we assume exists as capital from the initial condition x0 at time t. So now we consider arbitrary scalar functions. So we call it observables. This could be any small scalar function like a square function, exponential function, sinusoidal, or any other one. The Koopman operator is a composition operator that defined as the composition of the observable with the solution capital X. And this operator satisfies the semi-group properties. And one of the most important properties of the Koopman operator is linearity. So if we consider two observables, we can have, it's very easy to verify this linearity property. And another property is infinite dimensional. So because it acts on the scalar function space, so the dimension is infinite. And it's a strongly continuous semi-group linear contracting operator. So we may intuitively think of the linear system by collecting all the possible scalar functions from λ1 to lambda infinity, and it can be written in a linear system form, but note the variable z is infinite dimensional. But so as I say, but operating on an infinite dimensional space of observables. So here the operator A is something like an infinitesimal generator of the Koopman operator, and it can be used to characterize the spectrum property like we have done in the linear system theory. And although the Koopman operator is infinite dimension, but in sometimes we can use the finite dimensional subspace to provide the global information of the original nonlinear system. So we may have something like the eigenvalue, we call it Koopman eigenvalue, and a Koopman eigenfunction. There are some very particular scalar observables that can be project the original nonlinear behavior, nonlinear dynamical system to the new state space that behave with a linear one. So this is the solution for a linear system. If we can find scalar observable satisfy such property, we call lambda phi is observable as the Koopman eigenfunction, and the corresponding lambda is the Koopman eigenvalue. So in order to find such Koopman eigenfunction is equivalent to solve the partial differential equation like this one. We may consider a very simple example. There's a two-dimensional system, notably a square term, so it's nonlinear, and its behavior in the two-dimensional space x1, y1, and y2. So the behavior is quite nonlinear. But we can try to search for the three observables, x1, x2, and x1 square. And then calculating its time derivative, we got a linear system. And now we project it to the three-dimensional space. We can see the trajectory is satisfy the linear system trajectories. So we project from the two-dimensional nonlinear dynamical system to the three-dimensional, the higher dimensional system.
Oh, and we have a question.
Okay. So, thank you. So the question for the Koopman eigenfunction is that when we take it, it's mapping from the n-dimensional state space to a scalar.
Not really. The Koopman operator is defined on the infinite dimensional space because it's acting on the functional space. Yes. So here is we call it the Koopman eigenfunction. It's not the operator.
Yeah, but the range is scalar.
The range is for each of the elements is scalar. Yeah, that's we collect all the.
And this one is this is a complete representation, or in this case?
So here I consider the complex case.
Yeah, but for this example, you have three observables. Is it a complete representation of your nonlinear system? Sorry.
For this example, I first consider the three-dimensional case, and I will discuss the different cases.
Yeah, but is it an exact representation, or is
it's exact presentation because calculating this time derivative, we exactly got this linear system, and I will consider this example again and again.
So you're saying there are some cases where the representation is exact, right? Because before you said it's computational.
Yes. For general cases,
but for like say polynomial system, I suppose you can always. No.
Even for polynomial, it may be not maybe not possible to get finite dimensional. It depends, and I will just show you later. For some system, it's possible to do so, and we can get to exactly the same dimension as the original system with a linear behavior. Okay. So the Koopman operator can be used to get some criteria for global and symptotic stability. So we consider the autonomous system again, dot x equal to fx, and this hyperbolic equilibrium. It means the nonlinear system. For the nonlinear system, there is no central manifold. That means no eigenvalue on the imaginary axis. So the Jacobian is on the open left-hand side. If we can find n observables from phi1 and phi n, we collect it in a new vector field phi x. So if the system satisfies two properties, the first one, we call it a distinct eigenvalue. So that means the eigenvalue lambda I are different. And the second one is stability, that lambda I, they have the negative real part. So then the equilibrium x star is globally asymptotic stable. So we have the global property of the system. And this has been found in the Mori and the Mazik paper. So it's a very interesting paper published 8 years ago. Okay, so let me briefly summarize the Koopman approaches. In principle, the infinite dimensional operator acting on a space of observables, so it's the function of state space. But sometimes finite dimensional invariant basis can be constructed from which stability analysis is possible. And there's a very commonly used data-driven approach to collect the symbol of the trajectory xt and its time derivative x dot xt. And we try to find the nonlinear mapping phi from x to z, with the z finite dimensional, it's usually higher dimensional. And we can use some to calculate use some optimization to get to the matrix A, and we call this dynamic mode decomposition approach. And this is very useful in approximately getting some property system like stability, domain attraction, and many other topics. Okay, the second method we use a linear system to get to the nonlinear behavior. We call it a contraction analysis, and in some work also known as the incremental stability. So we consider the nonlinear system again, and the incremental exponential stability, it means for any trajectory of a given system from two different initial conditions, I call it x1, xb, it will converge to each other. So it's different from the traditional exponential stability, because in the standard one, we should define some equilibrium first. But in this case, the system may not have the equilibrium point. Okay, so this can be analyzed by using the size stability. We define an arrow between the two trajectory, and can be found in Angelis paper. And there's another popular method we call differential framework, using the contraction analysis by calculating the linearization of the system. So here I denote the infinitesimal displacement as delta x, and here is the Jacobian of the vector field. Okay, so please note this is different from the first order linearization. So it's an extension from for the standard linear system doing the quadratic Lyapunov function. We come back to the linear system x dot equal to fx again. This system is stable is that we can find a matrix, a positive defined matrix satisfy the Lyapunov inequality or Lyapunov equality. So that means we can imagine something like the energy function in a square form that is positive, and a long time its time derivative is negative, and the Lyapunov function will decrease to 0 over time. So the contraction analysis is an extension from this idea to nonlinear system. We come back to the original system here, delta x equal to x, and we have this time varying linearization. So here the Jacobian matrix we do the linearization along all the feasible trajectories, not a single one, but it should guarantee at along all the trajectory. The key result from Lumiere and Slotin, so this is a very famous paper in contraction analysis published more than 20 years ago. It's claimed the exponential stability of the associated linear time invariant system along the trajectory is equivalent to the contraction property of the original nonlinear system. So because for this linear time invariant system, the stability is easier to be obtained rather than we just analyze the original nonlinear system. And similarly, we can define the contraction metric with some quadratic Lyapunov function. Please note here, delta x is on the tangent space rather than original state space of x. And we can make its time derivative decreasing along time. So this should be held for any non-zero delta x. So it means the condition is true only if the blue part matrix, the blue matrix is negative defined. And here the contraction metric is a state-dependent family of the quadratic Lyapunov function of the delta x. So it's a state, it depends on the system state. And another good property of the contraction analysis is the condition is convex in the metric mx, even though the mx is infinite dimensional because we have some nonlinear function here. Okay, it provides a global convergence result. If the system satisfies the condition, we can conclude that all the system trajectory will converge to a single particular one. And we may intuitively imagine that for any, we can define the chain connecting a pi of system state. And for each infinitesimal part, it will converge to each other. So the condition provides the possible to get this convergence property. Okay, so the contraction has been employed in many different topics like nonlinear control well, convex optimization, and observer design. You can imagine observer design is exactly coincide with the contraction's definition. We hope the estimate of the state converge to each other. Okay, it's also being employed in the synchronization of nonlinear oscillators, and for example, in power system, and also using the convergence analysis optimization algorithm. And some people also using it for learning stable dynamical system and robust machine learning. Okay, so now let's come back to the Koopman operator and contraction analysis. So we find in the Koopman approach, is try to analyze nonlinear system by studying a nonlinear system, mapping it to a single but infinite-dimensional linear time invariant system. So in a contrast contraction, we study a nonlinear system by way of the infinite family of finite-dimensional linear time invariant system. So there are some differences. There are some differences and also some similarities. My question is there any connection between them? Okay, before finding the connection, let me do a slight extension of the Koopman criteria for global asymptotic stability. So as I have shown you that the Koopman criteria require a distinct eigenvalue, and for a given system, Jacobi may have some same eigenvalue, and this may bring some trouble. So I just extend the results a little bit and assume for the given system we have the hyperbolic equilibrium x star, and we can find capital N observables from phi1 to phi n, and I collect in phi, and the capital N should be larger than the original dimension of the system. So if we can, if the Koopman mapping satisfies two properties, the first one I call it the immersion. That's the Jacobian of the phi is full column ranked, and the second one called it stability, that the system satisfies the partial differential equation, and here the matrix A should be stable. So it's a slight generalization of the matrix result, and then we can conclude that the equilibrium x star is global and asymptotically stable. So in this extension, we do not need to require the matrix A is diagonalizable, and the emergent conditions is to pull back to the original x coordinate. Okay, and this idea can be extended to the infinite-dimensional with the capital A, N. Okay, so now let me show you our finding about the equivalence between two approaches. So here is our finding I write in plain language. For a given autonomous system, x dot equal to fx, two approaches, I mean the contraction analysis and Koopman operator, they are equivalent in nonlinear stability in a sense. If the system satisfying the Koopman stability criteria, what I mean, the immersion and the stability condition, then we can conclude the given system is contracting, and we can get the closed form of the contraction metric. And conversely, we claim if the given system is contracting, then we can get the analytical form with the finite dimensional Koopman mapping phi. So here is the formal claim of the equivalence between two approaches. We consider the nonlinear autonomous system x dot equal to fx, and the first conclusion is if the system, for the given system, we can find the Koopman mapping phi satisfying the immersion and the stability condition. The system satisfy the Koopman criteria for stability analysis. And additionally, the Jacobian of the Koopman mapping is uniformly bounded. Then the system is contracting. And the corresponding contraction metric is defined in this form. And the P is the solution of the Biamov equation. And this result, we can get the converse result. If the given system is contracting with a metric mx, and then we can always find a finite dimensional Koopman mapping phi satisfying C1 and C2. So in order to have the better understanding of the result, let me give you the sketch of the proof. So the first part is show if the given system is satisfying the Koopman condition, then we can conclude the contraction of the system. From the definition, if the system satisfies the Koopman stability criteria, then the system satisfies this partial differential equation. Here, phi is the Koopman embedding with the capital N dimension. And then we calculate the partial derivative of the x. So if we assume phi is smooth, then we got this. By just some very simple substitution, we got to the contraction inequality in this form. So it's relatively easy to get to this part. And intuitively, it defines the topology conjugacy from a nonlinear space to the linear space. So in the original low-dimensional space, the behavior is in a nonlinear way, but on the higher dimensional space, it behaves like a linear system. And our proof will boil down to the application of a contraction of the high-dimensional IoTI system. So a system in this high-dimensional system is contracting, and we can also conclude that it's also contracting on the low-dimensional nonlinear space. And this is a little and the converse part of the proof is more challenging because for the converse part, we assume the system is contraction, and we want to find an analytical form of Koopman mapping. So in order to do this claim, we need to solve the partial differential equation of this form. And the information we know that the system is contracting. This PDE is not very intuitive to solve, and my technical route is to reparameterize the Koopman mapping phi in this particular form with the identity part with another function tx to be searched for. So just substituting this one into the partial differential equation here, we got another partial differential equation in equation 16. Okay, and we need to, and here the matrix A is the Jacobian matrix at the equilibrium x star, and the function is in this form. Okay, so a very interesting finding here is the partial differential equation 16 is exactly the same as the partial differential equation in the so-called KK observer. So it's a very popular nonlinear observer. We call it Kazantzis-Kravaris-Luenberger.
So sorry, so I didn't get what you're gaining by doing this. I mean, 15 is a special case of 16 where H is 0. So what's the benefit of generalizing 16?
Okay, actually, this is not a generalization. So the aim we need to do here is solve the partial differential 15. We want to find a single solution. Any feasible one is okay. So I consider this very particular parameterization, and we find that this is possible to solve.
Yeah, but if you can solve it, can you solve the 16 for any h? If you can solve 16 for h equals 0, then you solve 16.
Yes.
So what's the benefit of producing this h?
By introducing the equation 16, I find that this one is always solvable with a Hurwitz matrix, with a stable matrix A.
Because of some property of H?
No, because the property of the matrix A is a stable matrix.
So the A is not the same as
no. Okay. So by introducing 16, we find that this PDE is always solvable with stable matrix A. And it's interesting to note this PDE is exactly the same one in KK observer. So what is KK observer? It's a state estimation technique for nonlinear system. So we have the annual system state X with the system output here, and assume the only access to the output Y, which is the function HX. And in the KK observer, we try to search for a coordinate change from the original X to the Z. It's very similar in the operator. And in the transformed dynamics coordinate, the dynamics is we hope it can be written in this form. It's contain a linear part with a nonlinear output injection. So this part only depends on the system output. For this case, we can implement the observer by copying the dynamics in the transform coordinate, like this form, the Kasai, and compile the system because the stable part, Kasai will converge to Z. If we can go back to the original coordinate X, then we can get the estimation annual X. And in the KK observer, the K task is solve the partial differential equation in this form. And let's come back to the Koopman problem, and we find the PDE is exactly the same. And one of the most important paper in KK observers proposed by Anzi and Pali from University, so they find for a stable matrix A, we have the analytical form of the solution of the annual matrix T. So we just utilize this result to solve our problem. So in our case, a feasible solution to the annual Koopman mapping can be get in this form. Unfortunately, this solution only defined some locally injective mapping phi. And our task is to guarantee the Koopman mapping is injective globally. So we need to do some modification to the obtain the Koopman mapping. And our solution is to obtain the Koopman mapping with this form. So we use the topology conjugacy in two coordinates and make the time go back a little, and we get this solution. And for sufficiently large Tx, we can guarantee the emergent arbitrarily large. So this is different from the way to impose emergent condition in PKL observer. In the observer design, the emergent condition is guaranteed by some observability, and in our case, by modification to this specific form. Okay, so let's come back to the two-dimensional example again. So we have the system is the square term, and in a previous example, we project this to three-dimensional to get a linear behavior. And using our method, it's possible to get a two-dimensional linear transformation. So we used our proposed equivalence relationship to define the Koopman mapping in this form by some straightforward calculation. We get to the Koopman mapping. There is a two-dimensional mapping in this form, and its time derivative is given by this one. So it's a linear system. We are able to get a two-dimensional coordinate change for the previous example. Okay.
What is the F?
Fx is the Jacobian of the system vector field. So here, and the star means this we choose its value at the desired equilibrium.
So sorry, my question is about the star. What is the
a star? Sorry, it should be Fx star. So
what is X star? No,
it's in the equilibrium. For example,
yeah, which equilibrium is that?
For this example, it's at 0, 0.
So because here in the last line you have f of x star. Mm-hmm. So what is f of x?
F a star.
So deal.
So f star, we calculate the Jacobian with the -1, 0, and 2x1 and max1.
So you're saying the last line and supposed to do a calculation of it. It's easy to verify.
This is verify. So because we do the coordinate change from the original x to this coordinate, and its time derivative is the coordinate in the new dimension, new state space, and behave like a linear system. Phi dot equal to a constant matrix multiplied by phi. So we can define the z equal to phi x, and then z dot equal to.
I'm just having difficulty parsing the question. So p, we have an expression of p, right? It's x1 and then -2. And then it's if I take the derivative of p. Okay, so I take the derivative of x1, so I guess x1 dot is -x1.
So the time derivative of the phi is a linear system. Okay. So use example, we can verify there are some exact equivalence between Koopman operator and contraction analysis. We're able to get the compact form for two cases. Okay, so some people may argue the result is very theoretical, and is the result is this equivalence useful? The answer is yes. So an implication of such an equivalence, I call it expressivity. That means all nonlinear contracting system, or equivalent can say, all stable nonlinear system can be learned in the Koopman framework. So, many people are working on the Koopman learning, but with such equivalence, we can say, if we have the good approximator, then all the stable nonlinear system can be learned by Koopman framework with finite dimensional state space. Okay, so I will apply the equivalence to two applications. The first one is learning contraction metric computed from data, and the second is system identification of nonlinear stable system. And well, the important part is propose the algorithm for the learning custom. Okay, the first one, learning contraction metric, what does it mean? For a given stable system, or we call it contracting system, and we assume we have a side of state trajectory data with the state x at the moment k and xk dot. And our task is to estimate the contraction metric at mx using the information of the data only. So for this case, we do not have the system vector field fx, but only have the data set. Okay, and this problem is very popular in recent years, and is used for robust motion planning and control for many different groups. And the Koopman operator can be used to simplify this problem to the linear system identification problem. It's a well-established field for the linear system ID. Our intuitive idea is that for a given system, if it's contracting, then we can always find the Koopman mapping and its inverse mapping with a Hurwitz stable matrix A, that the contraction metric can be parameterized as done in our proposed equivalence. So our approach to learn contraction metric is very similar to the DMD. We first select some basis function with a very high dimensional basis function omega x. And then we parameterize the Koopman mapping in this particular form with some annual vector phi to be searched for. And now the partial differential equation in our problem is discrete to this particular form with the annual parameter phi to be searched for. And we can use the data to solve the optimization problem to guarantee such matching. If we have the data set xk and xk dot.
Is this function, the choice of the base function,
yes, it's quite important. Okay, so here is a very simple numerical example. We come back to the two-dimensional system again. And if we have the trajectory at the time k and time derivative dot xk, and we can learn the metrics with the polynomial basis. And here's the result. We verify that the obtained contraction metric M, it satisfies the positive definite condition that's in this area. This is the minimal part of the real part of the matrix M is always positive. And the contraction conditions also satisfy that this is a negative definite. And there's a question, as you mentioned, so how to select the basis, or some people call it the dictionary or the Lantern features. Okay, so we try to extend the learning framework a little bit, and we consider this problem different from the side that is the system identification. We want to use the data side xk to learn a dynamical system. So for this case, it's more convenient to consider a discrete-time system, and we also consider the stable of the contraction system in this form. Our target is to propose a model class for learning stable discrete-time nonlinear systems. So for system ID, model class is a very important part. So model class, the algorithm, and how we can generate the data set are the most important three components in system ID problem. And we hope our proposed model class can be guaranteed to be stable. So this is important. Why? Because for many systems, we have some physical prior knowledge. So for example, we have a robot, for example, manipulator. We already know the system is stable, but due to the noisy data set or the optimization algorithm what we used, it may yield some unstable model, and this should not be acceptable. So for a stable system, we may get an unstable model, And the similar problem is like we have the controllable system, and using another noisy data set, we have the unstable, uncontrollable model, and we do not hope that happen. So we should have some built-in stability property of the model class. And we hope the proposed class is unconstrained in its parameters, because for a large-scale system, it's very hard to solve the constraint optimization problem efficiently. And our technical route should utilize our proposed equivalence between the contraction analysis and Koopman operator by embedding the system in a linear higher dimensional subspace. And this should contain all the stable system if the approximator we use is good enough. Okay, so in order to do to solve this problem, we extend the equivalence to discrete-time nonlinear system from the continuous dynamical system. And the discrete-time operator can also be defined as the composition composition operator. Here, the flow of the discrete-time system is just a vector field, and it's composed with the Koopman. I mean the scalable observables. And our equivalence can be extended to discrete-time system as claimed here. For the given discrete-time contracting system, this system is contracting if and only if we can generate the Koopman mapping phi such that the first condition, we have the sure stable matrix. So for the continuous time, we consider the Hurd stable, and with the partial differential equation. For the discrete time, it's become the sure stable, and with the algebra equation rather than PDT. And the second is exactly the same as we've done for the continuous time system. We hope the Jacobian of the Koopman mapping have the full rank and uniformly bounded. Okay, so here is our proposed model class. So we consider the system in a linear space and have the Koopman mapping to transform from the original nonlinear state space to a linear one, and we should guarantee we can come back to the original column with the Latin inverse of the mapping phi. Okay, and we should have some algorithm to search for the components in our model. It includes the stable matrix A, the Koopman mapping, and its Latin inverse. Before proposing the algorithm to do so, we need to properly parameterize the matrix A. So we hope the matrix A to be sure stable. You know, if you are familiar with linear systems theory, there are some convex condition like LMI, linear matrix inequality condition. But for a low dimensional system, it's very easy to use. But for higher dimensional, this type of the LMI problem cannot be efficiently solved. So we propose we call it direct parameterization of stable matrix A. There's an interesting finding. If this LMI satisfied, then we can say the matrix E inverse M F is sure stable. And in order to guarantee such type of the LMI, we can just parameterize this of its L transpose. So it's always positive dependent. And then we reparameterize the matrix A to some very straightforward calculation. And we can say for a given matrix A is sure stable if only if we can find the parameters L and R that satisfy this particular form. So this is a necessary and sufficient condition to guarantee a matrix A is sure stable. Okay, so now we try to parameterize the Koopman mapping phi. In order to have the generality, we make the observables in this form. There's a linear part, there's a nonlinear part. And for the nonlinear part, we consider the feed-forward fully connected neural network with rectified linear because of a rule activation function. So the Koopman model become the deep model by utilizing some some type of neural network. And we should also guarantee the origin as the equilibrium point by imposing this constraint that x equal to 0 as the origin. And we also need to parameterize the left inverse by L in a similar way. So now we formulate the system ID problem into the optimization. Since our model parameters are constrained, so we can optimize any differentiable objective function using auto-differential toolbox. And our optimization problem contains the simulation error and the reconstruction error. The simulation error means the information we obtain from the data side and the prediction using our model should be as close as possible. And the reconstruction loss is used to put the system back from the linear space to the from the nonlinear space to linear space to get the left inverse by L. And empirically, we found that minimizing simulation error in the high-dimensional phi space performed better than directly minimizing the simulation error next. So the simulation error is found in the high-dimensional nonlinear space. So we do this because some empirical results. Okay, in order to implement the optimization framework, we consider the very popular machine learning framework by the PyTorch and other optimizer. And in order to have the fast matrix power computation, we just simply assume matrix A is optimizable to get a faster computation speed. And in our simulation, we use the two-hidden layer and 5 nodes each, and the output dimension of 28. So here we use a very famous data site for learning, and it's a handwriting data, Lhasa handwriting site. So the human being manipulates the robot to write down some letters, so A, C, G, and we try to learn the model of the system. So the prior knowledge from this data site, we know the system is stable. Okay, so the left-hand side is our result by imposing the stability constraint, and the right-hand side is other method they do not consider constraint. So in some cases, we can see the results maybe have the very similar accuracy, but in some cases, if we do not impose the stability, the obtained model may lose stability due to the noise in the data set. And here is some comparison between training and testing error. And so here our method, we got the best one for accuracy. So at the end, let me talk a little bit about the extension to more general cases of the proposed equivalence. In the previous result, we consider the autonomous system, and our result can also be done for time-varying system. We consider the model .x equal to fxt. So here we have the dependency on time t. And the solution denoted as capital X from the initial moment X, initial state X, at the current moment t. Okay. So for this case, we need to extend the Koopman operator by introducing 2 parameters, t and original moment s. And the Koopman eigenfunction can be defined in a similar way. And here is the solution of a one-dimensional linear time-varying system. And this is equivalent to solve the partial differential equation with the time t. And we can also verify such equivalence between the Koopman operator and contraction analysis still hold true. Okay, and we also extend our result to the so-called orbital stability. And this problem is known as the limit cycle problem for an autonomous system .x equal to fx. And the limit cycle problem means that the closed loop generates some periodic oscillating behavior. So like something, the motion like this one. So this problem is very important in many engineering problems, like a bipedal robot. So you can imagine the robot is walking, and also the rotational electrical mechanical system like models, and it's also appear in biology. And the formal definition is the trajectory will come back to the position t after the moment t, capital T. Okay, so in order to analyze the problem, we extend the Koopman operator and contraction framework a little bit. In the Koopman operator, is similar to the hyperbolic equilibrium case, but we consider the n-1 eigenvalue, and the 0 value on the orbit should be satisfied. And for the contraction part, there is so-called the transverse contraction condition. And the condition, the difference is the contraction metric M. We do not assume it's positive defined, but it becomes the positive semi-defined. And we can prove for orbital stability, the Koopman operator condition for stability analysis and the transverse contraction analysis, they can imply to each other with the compactor form. Okay, so here is a very simple example for the living cycle in the induction model. Here is the model example, and we cascaded the model to the very famous field-oriented control problem is the factor standard method in industry. So for the closed loop, the system generates the living cycle, and we can analytically write down the Koopman eigenfunction. So this is a three-dimensional space. For the limit cycle case, there should be a 3 minus 1. So the Koopman function are 2, and we can use the Koopman eigenfunction to get a linear system. And correspondingly, use the equivalence, we get the transverse contraction metric in this form. And by verifying this concatenation, we can see the contraction condition is numerically verified here. And at the end, we are able to extend the problem from the dynamical system to the control system. We have additionally we have the control input U, and for this case we have the so-called control contraction metric. So if we consider for this case the condition change a little bit by considering the input U, and here G is the Jacobian for the vector field with respect to the input U. Okay, and we can also to analyze the control problem by defining the Koopman mapping with additional matrix U. So at the moment, we found if the system satisfies the Koopman controllability for the system, it implies the existence of CCM. But unfortunately, we cannot get the converse results at the moment. And in order to get the more general cases, the input matrix B is usually a function of state X. So for that case, people are considering the bilinear case. So for the, I just wrote here, the converse results are still open. Okay, so let me give a brief summary of the talk. In this work, we established the equivalence between two methods that analyze nonlinear system by means of linear system theory globally and exactly. They are Koopman operator and contraction analysis. And we consider the autonomous case and then extend to time varying living cycle and control system. And this theoretical founding is very useful for robust learning of a dynamical system that we can have built-in model stability for some system we already know they are stable. And the proposed model class are unconstrained in its parameters. And this is able to cover all stable systems. And in the future work, we hope to extend the learning framework for control system. And we hope to close the gap on the converse results in the closed system. And we hope to integrate the proposed results in control and estimation problem to solve more complicated practical problems. Okay, thank you. And I'm ready to get any questions.